far beyond the familiar stars of our night sky. In a quiet region of the constellation Leo, a faint change in infrared light reached Earth after traveling for more than a century through the darkness of space. At first glance, it appeared to be just another collection of data, one more stream of numbers among the trillions gathered by humanity's most powerful space telescope. But hidden within that light was something no one expected, a chemical signature associated not with rocks, oceans, or storms, but with life itself. The James Webb Space Telescope had detected a world so remarkably balanced and chemically intriguing that scientists reached a level of confidence rarely seen in astronomy. Not merely a possibility or a distant hope, but a planet that appeared potentially habitable and, in some respects, even more favorable to life than Earth. What Webb discovered did not simply suggest that life might exist somewhere in the universe. It hinted that we may have found one of the strongest candidates yet. The breakthrough arrived quietly, buried within infrared observations collected as a distant planet passed in front of its host star. As the starlight filtered through the planet's atmosphere, certain wavelengths were absorbed, leaving behind a unique spectral fingerprint. Scientists first identified familiar molecules, water vapor, methane, and carbon dioxide. Each one was significant, each one an important clue pointing toward a potentially habitable environment. Then came the molecule that changed everything, dimethyl sulfide. On Earth, this compound is produced almost exclusively by living organisms, not by volcanoes, lightning, or ordinary chemical reactions. It is considered one of the most intriguing potential biosignatures because its primary known source is life. Even more remarkable was the strength of the signal. The probability that the detection was simply a statistical error fell below 3 chances in 1,000. In a scientific field where uncertainty is expected and extraordinary claims demand extraordinary evidence, that level of confidence immediately attracted worldwide attention. The planet, known as K2-18b, orbits a red dwarf star approximately 120 light-years from Earth, well within the region where liquid water could exist. Unlike the rocky Earth-like planets scientists once believed were the only promising homes for life, K2-18b belongs to an entirely different category. It is a super-Earth, larger, more massive, and surrounded by a thick hydrogen-rich atmosphere. Surprisingly, rather than making the planet hostile, that atmosphere may actually create conditions favorable for life. K2-18b is not balanced on the narrow edge of habitability in the way Earth is. Instead, its environment appears unusually stable. Scientists estimate that temperatures could remain warm enough to support liquid water while avoiding the extreme heat that would cause oceans to evaporate. This stability may result from the planet's thick hydrogen atmosphere, which acts like an enormous insulating blanket, trapping heat and distributing it more evenly around the globe. Unlike Earth, where temperatures fluctuate dramatically between day and night or from season to season, K2-18b may experience far more consistent conditions. Because the planet is likely tidally locked, one side permanently faces its star while the other remains in eternal darkness. Yet atmospheric circulation may keep even the night side warm enough to maintain liquid water. Gravity also plays an essential role. With nearly 3 times Earth's surface gravity, K2-18b can retain its dense atmosphere far more effectively, preventing it from escaping into space as happened on Mars billions of years ago. What seems extreme from a human perspective may actually provide ideal conditions for sustaining life. Strong gravity, a thick atmosphere, and stable temperatures together create an environment where life would not constantly struggle to survive, but could instead evolve and diversify over immense stretches of time. The planet's host star is a red dwarf, much smaller and cooler than our Sun, yet vastly longer-lived. While our Sun will eventually expand and make Earth uninhabitable, red dwarfs can continue burning steadily for trillions of years. That means any life that develops on a planet like K2-18b could have almost unimaginable amounts of time to evolve. K2-18b completes one orbit every 33 days, remaining close to its star while receiving nearly the same amount of energy per square meter that Earth receives from the Sun. This places it firmly within the habitable zone. However, there is one major difference. Around red dwarf stars, the habitable zone can remain stable for far longer than it does around stars like our own. When this long-lived habitable zone is combined with a thick atmosphere that protects the surface from harmful radiation and redistributes heat across the planet, it becomes clear why scientists are reconsidering long-held assumptions about habitability. This discovery suggests that Earth-like planets may not necessarily be the best places to search for life. Instead, The universe may favor worlds that are larger, warmer, and more environmentally stable than our own. What truly makes this discovery extraordinary is not only the planet's location or its temperature, but also the unusual chemistry of its atmosphere. The detected gases exist in a state of chemical imbalance. On a lifeless planet, these molecules would naturally react with one another until they reached equilibrium and disappeared. Yet on K2-18b, they appear to persist in significant quantities. On Earth, this kind of atmospheric disequilibrium is maintained almost entirely by biological activity. Living organisms continuously release gases into the atmosphere, preventing chemical equilibrium from being reached. K2-18b appears to display a similar pattern. The apparent absence of ammonia, a compound scientists would normally expect to find in a lifeless hydrogen-rich atmosphere, strengthens this possibility even further. Something may be actively removing it. If this interpretation ultimately proves correct, then humanity is not merely observing a planet where life could someday emerge. We may be observing a world where life is already reshaping its atmosphere on a planetary scale. A living planet breathing across interstellar space, its biological activity detectable from a distance of 120 light-years.